Okay, so as always, please type your name into the chat now that I've started the recording, because that's going to be your record for attendance and for future data distribution. Okay, so welcome everybody, and we'll let more people in as they come in. Okay, I know we've been having a lot of time off. Weeks. We last week we didn't meet, and 3 weeks ago we didn't meet. We're entering a stretch now where we will meet every week for a while. I think the next 4 weeks in a row we're going to meet according to the schedule before we have another week off. Okay, so all right, so thank you and welcome to everybody one more time. So I want to go back and spend a little bit of time on review because we had to rush things a little bit last time. And I have a feeling that this topic of logic is familiar to some people, but I think it's not as familiar to as many people as some of the earlier topics. And it's one of the reasons why I think people voted to spend some time on it. So I want to spend a little bit of time recalling what we did last time, especially since it was 2 weeks ago. So if we recall, I looked at the logical reasoning curriculum. This is from page 43 of the math curriculum document. Okay, so this is from page 43 of the math curriculum document that I sent out over the chat room a while ago. That the main aspects of logical reasoning that we need for the curriculum are statements, implications, converse, equivalence, negation, and valid argument. So today we're going to finish getting through all of these. We spoke about statements and implications and converse a little bit last time and a little bit about negation. We're going to spend some more time today on equivalence and on valid argument. And because, it's a workshop for teachers and not for students, we're going to go somewhat beyond these just the basic topics on the curriculum document, and that will probably go into next week a little bit. We'll probably spend about half of the time next week finishing up logic before we go into the next topic. Okay, but before we move on to any of that, let's just recall something that we did last time. So, in more detail, so last time we talked about what a logical reasoning workshop could start with, and we had some basic questions that we discussed and that we'll recall. So the most basic question is maybe what is a statement? Following from that, we have how can statements be logically connected? What are laws giving valid implications? What is the process and meaning of negating a statement? And what are the formal tools that can help us with this? Right? A lot of times when you're doing logic, especially if you start off with it, you can feel like you're not really doing mathematics. You're just speaking about words and giving reasoning. And I mean, well, part of the answer is that that is doing mathematics, right? Logical reasoning is the core of mathematics. It's what you do when you do mathematics. But also there are ways of formalizing everything that make it look a little bit more like traditional math. And we'll talk about some of those formalization procedures today. Things like truth tables and two-column statement reason proofs that are going to make everything look a little bit more formal than it did before. Okay, so we also had a larger goal, which is that participants should be able to solve word problems and puzzles based on logical laws. And then for a longer workshop, we might also try to include quantified statements involving for all and there exists, as well as applications of logic in computer science. We're not going to talk about those today, but these are possibilities for the first half of next week. Okay, so these are possibilities for the first half of next week. Okay. So let's just recall last time we talked about what a statement was. So recall that a statement is a sentence that is either true or false, right? So 2 plus 5 equals 8 is a statement, right? It's a false statement, but it is a statement. A non-example would be something like x plus 5 equals 8, right? Because we can't say whether this is true or false. We can't say whether it's true or false because it depends. Some more people come. It depends on the value of x. Okay, so sentences like this are outside of the realm of logic. Okay, they're part of mathematics, but they're not part of formal logic and logical reasoning, which is what we're really talking about, because this thing is not a statement. And when we deal with logic, we deal with statements that are either true or false. So something like this is neither true nor false, and so we can't really treat it like a statement. Okay. So everything that we deal with is going to be statements that, maybe they're true statements, maybe they're false statements, but they have to have it has to be reasonable to give it what's called a truth value. So when I say the word truth value, what I mean is true or false. Okay, those are your possible truth values. Okay. And I don't want to go over it in so much more detail, but we had these other examples last time of things that are not statements. So, for instance, a question is not a statement. A command is not a statement. A statement is just a declarative assertion that something is true. Now, and you may be wrong about that, but it's still a statement. But when you talk about a command or a question or things like that, these are not statements claiming that something is true. Okay, so those also, do not fall within the realm of statements. We don't consider them statements. Any questions about statements here? I know we did this in some detail last time. I don't know if people need that detail again or if it's fine to just move on from here.
Yes, Graf.
Okay.
I
Yes.
think I think because we have the notes and the video, people will just review. I
Okay.
think we should move on here.
Great. Okay. Let's move on. Okay, so I also want to recall all of these logical connectives that we talked about last time. So, logical connectives are ways of building more complicated statements out of simple statements. By the way, these simple statements, I didn't use this word last time, but a simple statement, these are sometimes called atoms in analogy with chemistry and physics, where an atom is taken as the building block of all matter, right? So, in the same way, these simple statements are the building blocks of compound statements via using logical connectives. And as you can think of logical connectives as like chemical bonds between atoms. And so sometimes we call them atoms or atomic particles or atomic statements. So you'll see me sometimes use this word atom for a simple statement, and logical connectives are the way that we make more complicated statements out of simple statements. So there are five main logical connectives. I'll go over them, but we did do this last time, so I'll just go over them for a brief review. So the first one is or, and the symbol for that is a V, capital V. And the meaning in logic is that if P and Q are statements, then P or Q is true exactly when at least one of P or Q is true. So it's okay if P and Q are both true, and it's okay if just P is true, and it's okay if just Q is true. So if any one of them is true, then we say that P or Q is true. Similarly, and where we use the symbol, this upside down V, if P and Q are statements, then P and Q is true exactly when both of P and Q are true. Okay, so it's kind of intuitive based on the language. The only way that P and Q is going to be true is if both P and Q are true. Okay. Then we had implies. This is also sometimes called if then. So sometimes also called if then. So if P and this one is a little more confusing. So if P and Q are statements, then P implies Q. We think of this as true as long as it's not guaranteed to be false based on what P and Q are. What would show that this is false? Well, P implies Q. It should mean that if P is true, then Q has to be true. That's what it means for P to imply Q. So if P is true, then Q is true. So if you had that P was true and Q was false, then the implication would certainly be false, right? You couldn't have a true thing implying a false thing that, contradicts the meaning of the word implies. That would make it nonsensical. So this statement is definitely going to be false if P is true and Q is false. And then in logic, we basically take it to be, as long as it's not certainly false, we just take it to be true. This turns out to be a convenient way of doing things. So in fact, we say that this P implies Q is always true as long as we don't have that P is true and Q is false. If P is true and Q is false, this thing is false. Any other combination of the falsity and truth of P and Q is going to make this statement true. So if P is true and Q is true, then the implication is true. If P is false and Q is true, the implication is true. And if P is false and Q is false, then the implication is also true. Okay, there's only one case where it's going to be false. So this is how we view these implications. We have another thing, which is if and only if, which is the same symbol, but it's an arrow with two heads, a head in each direction instead of only a head in one direction. And we say P if and only if Q, or you can sometimes read this as P is equivalent to Q. That's going to be true exactly when either they're both true or they're both false. So this statement is really saying that this statement can only hold when P and Q have the same truth value. So P if and only if true means if P is true, then Q is true, and if P is false, then Q is false. Q is true, then P is true, and if Q is false, then P is false. Okay, so it's true exactly when P and Q have the same truth value. And then lastly, we have not, right? All of these connectives connect two statements. The not or the negation is just about one statement, and it just negates the statement, which means that if P is a statement, then not P is true exactly when P is false. Okay, so it's the opposite statement of P. So if P is the statement, it's raining, then not P is the statement, it's not raining, right? One of them is true, the other one is false. And these are the simple connectives, but you can combine, right? I mean, if I have statements P, Q, and R, I can write, P and Q implies, R or not Q, biconditional R and not P, right? I mean, who knows what this statement really means? It's something complicated, but the idea is that you can combine these logical operations in the same way that you combine arithmetic operators. Like you can use plus and minus and times and divided by, and you can make some complicated expression with lots of parentheses and using lots of symbols over and over again. You can do the same thing with logical connectives. So this means, evaluate the statement R and not P, evaluate the statement R or not Q, see if those have the same truth value. That's the truth value that gets plugged in here. And now evaluate the statement P and Q, and then, see what the truth value of this implication is. Okay, so depending on what truth values you substitute for P, Q, and R, this entire compound statement will also get a truth value, right? Because P, Q, and R are the atomic statements. This here is the compound statement. It's still a statement. It's still going to have a truth value. Okay? So for instance, if P, Q, and R are all true, well then P and Q is going to be true. So this is true. R or not Q is going to be true because R is true. R and not P is going to be false because P is false and R is true. So here we have true if and only if false. They don't match. So that means this entire thing here is going to be false. And we have then true implies false. And that means that the entire statement is false, right? Because an implication is false exactly when the first thing is true and the second thing is false. Okay, so we'll do this more carefully later on. Don't worry if that went a little bit fast for you. But the idea is just the concept that if P, Q, and R have truth values, then you can combine them using as many symbols as you want into some big compound statement that will also have a truth value. And you can try to evaluate whether that's true or false based on whether the input atomic statements are true or false. Okay, so from these logical connectives, you can make much more complicated logical things, right? Or you can just combine, you can do more, more basic combinations. You can do something like P or Q or R, right? I mean, that's another way of combining these, right? That's going to be true if and only if any of them is true. If any one is true, then it's true. If they're all false, then this is going to be false. Okay. So these are just examples. All right. Any questions about the logical connectives? This is still mostly review from last time.
Yes, good afternoon, good morning, Dan.
Yes, Enoch.
Yeah, I have a question on this implication.
Hmm.
So, yeah, so should we say or can we say the true or false stated depends actually on statement Q? For example, when you are giving statement P and that is statement Q for the implication.
Hmm. Yeah, it depends on both, right? And in particular, this implication here is not symmetric, right? You can't reverse the roles of P and Q. Like here, everything is symmetric. P or Q, you can just switch them. P and Q, you can just switch them. But P implies Q is not the same thing as Q implies P. We did this last time. I'm going to recall it quickly also. But yes, it definitely depends on the truth value of both P and Q.
Okay.
Okay. Other questions? Okay. So give me 1 second and then we'll move on to the next. That's not what I wanted to do. Okay. Okay. So let's move on. So I mentioned this briefly last time, but one of the nice ways of summarizing these properties of logical connectives is that you can summarize them in what's called a truth table. So here's how I'm going to write a truth table. Um, I'm going to write a big box over here. And so the truth table is going to have columns. So I start with the columns for my atoms. So my atoms here are P and Q, right? So these are going to be my atoms. I start here with this. And then I'm going to have, because I have two atoms, I'm going to have 4 rows of the truth table beneath the atoms. And what I'm going to have here for these rows of the truth table is every combination of true and false that you can have for P and Q. So I can have that P is true and Q is true. I can have P is true and Q is false. I can have P is false and Q is true. Or I can have that P is false and Q is false. And so now what I can do in this truth table is I can make a new column for every way of combining P and Q, right? So I can start with P or Q. That'll be its own column. P and Q. P implies Q. P if and only if Q. And lastly, not P. Right, so these are all, I'm just repeating all of the logical connectives from the previous slide, right? This is all of these five things. And the properties of all of these connectives can be written down in this truth table. So what happens is if our atomic statements, if P and Q have these values that we're assigning, so either true, 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 false, false, true, or false, false, then that will give each of these statements a true or a false value. So for instance, for P or Q, right, we've seen that if P and Q are both true, then this is true. If P is true and Q is false, this is true. If P is false and Q is true, then this is true. But if P and Q are both false, then this is false, right? Because the or is false only when both of the inputs are false. Similarly, for P and Q, if they're both true, it's true, but we know that for and, it requires both of them to be true to be true. Otherwise, if either one of them is false, then it's going to be false. So for these last three columns, here Q is false, so the and is false. Here P is false, so the and is false. And here P and Q are both false, so the and is also going to be false. Okay. Now, what about P implies Q? Well, we saw on the previous page that that is going to be true except when P is true and Q is false, right? This is the implication that you can't have a true thing imply a false thing. That, completely contradicts the meaning of the word imply, right? So true things don't imply false things. So that's going to be false, but our convention is that every other arrangement gives you a true value for this conditional. So P, if and only if Q, we said this was true exactly when P and Q have the same truth value. So if they're both true, it's going to be true. And if they're both false, it's going to be true. But in these two rows, one is true and one is false. And over here, we have that one is true and one is false. So over here, we're going to have that the biconditional, this is called a biconditional, is false because one of P or Q is true and the other one is false. And then lastly, we have not P, which is going to be true exactly when P is false and vice versa. So how do we fill in this last column for not P? What are the values we're going to get? So yeah, what values do we put in the squares there? Right, anybody? FF. Okay, yes, I see. FF, right. So it starts with FF. So Moscow, thank you. Right. So the first two will be false because um, P is true. And then for the bottom two rows, there P is false. So that means not true is going to not P is going to have to be true. Right. Okay. So the benefit of a truth table is that instead of having all of these words with all of these definitions here, which I know some people like learning with words, so it's good to have them there, but this gives a very concise summary of everything on the previous page, right? This gives you all of the logical connectives and it tells you exactly how they work, right? Because you have the four rows represent all of the possibilities for the inputs. And then with the logical connectives, you have now a table that tells you exactly how to evaluate them. And so you may already be able to see the connection to computer science, right? Computer science or computer architecture, right? Every switch is on or off. It all works in binary. So you think of everything as a zero or a one. And you can think of, one as true and zero as false. And you can think of ways to transform ones and zeros into each other as given by these logical connection gates. So there's something called an OR gate and there's something called an AND gate that will do the correct transformations to turn switches on and off. And this is kind of how basic computer computation works. So again, if this is something that people want to go into more next week, I can spend some time talking about it.
Yeah, that.
Yep.
Yeah, in the table, I think you left out the negation of P.
I left out negation of Q. That's true. If you want
The negation
of
of Q, yeah, Q.
yeah, so you could add another row for that if you want. But the point is, once we have this row, this tells us how negation works, right? Because it already tells us when the input is true, the output is false. And if the input is false, then the output is true. So if you want to put in another row for not Q, that's a good exercise to do on your own. But it's not really, the definition of not is already contained here in this column. So But if you want to, you can put in an extra row for not Q. That's fine. Okay. Any questions about the table? Okay. Maybe actually I'm going to add one more page about a truth table. You can use a truth table to evaluate more complicated statements. So let's say that we have a statement like P and Q implies uh, P and Q implies Q and P. Let me make some statement like this. Okay. Well, I can make a truth table for this statement by building it up. Um, so let me do, what do I mean by that? I'm going to have P and Q here. I'm going to still have my 4 rows. Sorry. Still have my 4 rows here. And now I'm going to build up the statements I need. Well, I've got P and Q, and here I have Q and P, and then here I have the final statement. P and Q implies Q and P. So the first 2 columns are always the same. TTFF, TF, TF. I mean, you can write them in any order you want, but this is the traditional order. So now P and Q we've already seen. It's true when they're both true, and it's false when they're both false. Well, Q and P is the same thing as P and Q, right? It doesn't matter which order you do the and in. So the column for Q and P is going to look just like the column for P and Q. And now we have this. P and Q implies Q and P. Well, let's see what we have. Well, in this column, in the top row, we have true implies true. That's true. In the next row, we have false implies false. That's also true. I've seen that from before. False implies false is true. And then actually the bottom 2 rows are the same. It's false implies false and false implies false for both of them. So in fact, this statement is true no matter what truth values P and Q have. So this statement, P and Q implies Q and P, this is always true, no matter what the inputs for P and Q are, and this is sometimes called a tautology. A tautology in logic means a logical statement that's always true, no matter what the truth values of the atomic inputs are. Okay, so you can combine them in a way to get something that's always true. And a tautology, I mean, in philosophy, means something that's always true. And this makes sense. No matter what your statements P and Q are, P and Q certainly implies Q and P, right? You know, if it's raining and it's warm, that certainly implies that it's warm and it's raining, right? I mean, the 2 statements mean the same thing. So it doesn't matter whether it's actually raining or whether it's actually warm, just the statement, if it's raining and it's warm, then it's raining, then it's warm and it's raining, certainly, is true. Okay? It's just logically a tautology. Okay? So this is a way you can use a truth table to compute compound statements starting with simple statements. You just build up whatever's in the parentheses, and then eventually you put the statement you want in the last column, and you can build up to what the truth value of that statement is. Okay, any questions? Okay, good. Okay, so one more recalling from last time, this converse and contrapositive. Suppose that we have a statement of the form P implies Q. So if it's raining, then there are clouds in the sky. P is the statement it is raining, and Q is the statement there are clouds in the sky. And turns out each such statement has a converse as well as a contrapositive. The converse, by definition, is the statement Q implies P. You switch the order. It says if there are clouds in the sky, then it's raining. And this is not equivalent to the original statement, right? And the original statement is clearly always true, right? If it's raining, then there are clouds in the sky, right? It doesn't rain when the sky is clear. But the converse is not true, right? Just because there are clouds in the sky doesn't necessarily mean that it's raining. Okay? It could just be a cloudy day, right? So, all right. So we see that a statement and its converse are not the same. And this is a very common fallacy that people make when they argue incorrectly about things, is to confuse a statement with its converse and treat them like they're saying the same thing. And they're really not saying the same thing. What you do have instead, though, is that the contrapositive of a statement is equivalent to the original statement. So the contrapositive of P implies Q is you take the converse, but then you also negate both of them. So it's the statement not Q implies not P. And this is equivalent to the original statement. And if you think about it, logically, to use the word for a little bit, it makes sense, right? To say if it's raining, then there are clouds in the sky is the same thing as saying if there are no clouds in the sky, then it's not raining, right? Both are ways of saying that for it to rain, it is necessary for there to be clouds in the sky, right? It's necessary that there are clouds in the sky, meaning if you don't have clouds, you can't have rain, okay? So both the statement and its contrapositive mean the same thing. And maybe I'll give an exercise here. Show that P implies Q and not Q implies not P have the same truth table columns. Okay? So meaning we already know you have for P and Q, we've already done P implies Q. So do a column for not Q implies not P. If it's your first time doing this, you'll probably first have to make a column for not P, which we already have, and then make a column for not Q. And then you'll put them both together in this implication. And what you'll show is that P implies Q and not Q implies not P have exactly the same column in the truth table. That means that they're equivalent to each other. Because no matter what the assigned truth values of P and Q are, no matter what the statements are, this is going to be true exactly when this is true. And this is going to be false exactly when this is false. Okay, and that's what it means for two things to be equivalent. They should have the same truth value no matter what the inputs are. Okay, so this is a good little exercise to show that when you make a truth table, that P implies Q and not Q implies not P are going to have the same truth table columns. All right. Any questions? Okay. Okay. Um, okay, Victor, I'm sorry. I'm sorry you're not feeling well. I hope you recover quickly. Okay, so let's talk a little bit more about this equivalence, right? Two logical statements made out of atoms like P and Q and logical connectives are called equivalent. This is what I said. If one is true exactly when the other one is true. And equivalently, if they have the same, I shouldn't say the same truth table, I should say the same truth table column. Okay, so we've already seen one example of equivalence, which is the contrapositive, right? We've seen that P implies Q is equivalent to not Q implies not P. So let's just give maybe another example of two equivalent statements. So this is one that we saw last time. So I think we showed that not P and Q, sorry, not P and Q is equivalent to not P or not Q. Okay? So if you think about this intuitively, then it kind of makes sense, right? Not P and Q means that somehow P and Q are not both true, right? That's what it's. P and Q means they're both true. Not P and Q means they're not both true. Well, what does it mean for P and Q not to both be true? Well, it means either P is not true, that's the statement not P, or Q is not true. Okay? But let's do this formally with a truth table. So formally, I'm going to make a truth table, and we're going to show that these two things have the same column. Right? So I'm going to start, let me make 4 rows. Okay, so we start with P and then Q. Now here we have P and Q. And now I can have not P and Q. Sorry that the writing is a little small. I'll try to make this a little bigger. Not P and Q. Next, we'll have not P. Now I want to build the other statement, right? We have not P. I'll have not Q. And then lastly, I'll have not P or not Q. And these are the two columns that we want to show are the same, right? Not P and Q. And this over here is not P or not Q. Okay, so let's fill in the table, right? We always started off the same way. True, 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 false, false, true, false, false. This is every possible way we can fill it in. P and Q we've already done, right? It's true when they're both true, and it's false in every other instance. So true, false, 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 right? Now, what's this column? This is not P and Q. So if this is P and Q, what we're doing is negating this column, right? Which means whenever this statement is true, the negation is going to be false. And whenever this statement is false, the negation is going to be true. So if here is true, that becomes false. When it's false, it becomes true. When P and Q is false, it becomes true. And when P and Q is false, right? So maybe I'll just put little green arrows here that we show where we're getting this from, right? It's always switching the truth value when you have a negation. Think of negation as kind of like multiplying by -1. It switches the sign, it switches the value. Okay. So now we have not P over here. So basically we're done building this statement. Now we're going to go try and build this statement. Well, not P is going to be the same as P, but switched, right? So instead of true, true, false, false, we're going to have false, false, true, true, right? So we've already seen this. Oh, oops, let me do this in blue. So false, false, true, true. Next, we have not Q. Well, Q is true, false, true, false. So not Q has to be the opposite. So it's going to be false, true, false, true. True, false, true. And then lastly, we have not P or not Q. So that's going to be true exactly when one of these statements is true or both of them is true. That's what or means. Okay, here they're both false, so we're going to have false. Here, not Q is true, so the or is going to be true. Here, not P is true, so the or is also going to be true. And here, they're both true, which means the or is going to be true. And so now let's look at these two columns. Well, not P and Q has this column, false, true, true, true. And not P or not Q also has this same column, false, true, true, true. So that tells us that they're equivalent, okay, because they have the same truth table column that they correspond to. Okay, so formally, this is the truth table column that represents both statements. Since they're both the same, we call them equivalent statements. Okay, so when we have equivalent statements in logic, what we mean is that they have the same truth values no matter what the input truth values are. Okay, and so you can do the same thing as an exercise on the previous page, which I'm not going to do, but you can do it. You can do the same exercise with P implies Q and not Q implies not P. You do this as a truth table column, you do this as a truth table column, you show that they're going to be the same. All right, any questions on this? Okay, it's clear. Okay, let's move on. Okay, negation. So here we have equivalence. What's negation? Negation is the opposite of equivalence, right? A logical statement is the negation of another logical statement if and only if when one statement is true, the other one is false, and vice versa, right? So I think so. Actually, yeah, I guess we saw last week that the negation of P or Q is not P and not Q. So another way of saying this, maybe I'm not going to do it with truth tables because we already did something equivalent with truth tables. Another way of saying this is that not P or Q is equivalent to not P and not Q. Okay, this is another exercise that you can do with truth tables. Yeah, you can just do their columns and show that they're the same. So now here's another thing. So can we use a truth table to negate the statement P implies Q? Right? So another thing is saying is that another way of phrasing this is what statement is not P implies Q equivalent to? That's what this really means, right? Now, of course, you can just write not P implies Q. That's a perfectly good statement. But sometimes with these negations, you want to simplify it. It's just like in algebra. If you have an expression with a lot of parentheses, you can simplify the expression by using the distributive law and, doing various operations to get rid of the parentheses. You do something similar in logic. Is that when you have parentheses and negations and stuff like this, you can simplify the expression to try to get rid of the parentheses. So let's look at this, right? So I'm going to make another truth table. I'll make it bigger once I draw it. Okay, so we start as usual with P and Q. True, 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 false, false, true, false, false. Okay, so now we have P implies Q. I'm going to just first try to do a truth table for this statement, right? So P implies Q, we've already seen that. It's true, false, true, true, right? It's true as long as you don't have P is true and Q is false. So the negation of P implies Q is going to be just the opposite of this column, right? So true becomes false, false becomes true, true becomes false, and true becomes false, right? So we're just switching the truth value for all of these. And so now we want to know, what is a statement that is equivalent to this? Well, let me look at this column, right? Well, this column seems like it's only true here. So something that's true only once out of 4 times, that looks like an and statement to me, right? That looks like an and statement to me, right? So true over here, when is this going to be true? It's going to be true exactly when P is true and Q is false. So that should be the same thing as P and not Q. Well, you know what I'm going to do is I'm going to give myself one extra row, one extra column of my truth table. Maybe I'm just going to do a column here just for not Q. That's easy. It's the opposite of Q, so that's going to be false, true, false, true. And now I'm going to have P and not Q, right? By looking at this column over here, sorry, it looks like this whole thing is true exactly when Q is false and P is true. So that should be P being true and not Q being true. Q is false is the same as not Q is true, right? So let's look at this. We've got P, this column, and not Q. So here you have true and false. That's going to be false. Here we have true and true. That's going to be true. Here we have false and false. That's going to be false. And here we have false and true. That's also going to be false. Just need both to be true. And now we see again that this column over here, not P implies Q, is the same thing as P and not Q. Okay, so what we say is that the negation of P implies Q is P and not Q. So the negation is actually not phrased in terms of a if then or an implies at all. It's phrased in terms of an and statement, sometimes called a conjunction. Okay, so the negation of P implies Q is actually P and not Q. Any questions? Okay, so maybe let me just state this just so that it's clear. So I'm just going to state this. It says negation of P implies Q is P and not Q. Okay, no questions? Okay, let's move on then. So that's negation. So equivalence and negation are the opposite of each other, right? Two statements, they're equivalent if they have the same truth table column, and they're negations if they have the opposite truth table column. Or in other words, if not one of the statements is equivalent to the other. That's another way of saying they're the negation of each other. Okay, so you can always do the negation of a statement by just putting a not and then putting the statement in parentheses. But that doesn't really do anything. The idea is, can you simplify that? Okay, and that's this negation is one of the ways you simplify this. So let me actually write this just as a summary of how to do nots. Not P or Q is equivalent. I'm going to use this equivalent sign, which is an equal sign with an equal sign with 3 bars. This is the symbol that you use for equivalent in logic. Not P or Q is equivalent to not P and not Q. Not P and Q is equivalent to not P or not Q. So it's kind of like a distributive law, but you also flip the and to an or the or to an and. Not P implies Q is equivalent to P and not Q. Not turns out that not P, if and only if Q, this is actually equivalent to not P, if and only if Q. Turns out these two things are equivalent. This is again an exercise. But all these exercises, you can just prove them using truth tables. Right? So this is again an exercise. And then lastly, not P is the same thing as P. Right? To negate not P, you just have P. So this is how you negate every logical connective, right? Once you know how to negate logical connectives, you can then just do everything. You can do everything step by step using that. Okay. Okay. So now let's move on to arguments. Okay, so we've done equivalence, we've done negation, we've done converse, we've done contrapositive, we've done statements. All of this stuff gets put together in order to do what's called logical deduction or logical arguments. So there's lots and lots of different laws that you can use. This is not exhaustive, but most of these are the main laws that you're going to need to use to do any kind of logical proof. So I want to state some of the most common logical laws that can be used to deduce statements from other statements. Okay, so maybe the most fundamental reasoning, is possibly the most fundamental human reasoning process in our species is what's called modus ponens. Okay? And modus ponens means that if you know that P implies Q and you know P, then you know Q, right? If you say that, like, all dogs have hair and I am a dog, then the implication is I have hair, right? That's so meaning if you're a dog, you have hair, and you're a dog, that means you have hair, right? So this is the most basic implication. If you have an implication, P implies Q, and you have P, which is kind of the hypothesis, then you get Q, which is the conclusion. Okay, so if you know P implies Q and you know P, then you can deduce Q. So the kind of companion of this is something called modus tollens. So if you know that P implies Q, and you also know that Q is false, meaning you know that not Q is true, then you can deduce not P, right? So if you're a dog, you have hair, and you know that you do not have hair, that means you can't be a dog, right? So if you don't have hair, then you're not a dog, right? Because if you were a dog, you'd have to have hair. Right. So this is so if you have P implies Q and you know that the conclusion is false, then the hypothesis must also be false because you're accepting that the hypothesis implies the conclusion. Okay, so that's called modus tollens. Note that the other laws do not work. So if you know that P implies Q and you know Q, you cannot conclude P, right? If P is I'm a dog and Q is I have hair, and if I know that if I'm a dog, I have hair, then just because I have hair doesn't mean I'm a dog, right? All dogs have hair, but not everything with hair is a dog, right? I could have hair and I can be a person, right? So you cannot conclude the hypothesis from the conclusion. Okay, this is a very, very big, issue in scientific papers. You have a hypothesis, you need to conclude the conclusion from the hypothesis. You can't conclude the hypothesis from the conclusion. Okay? All right, so you can go if the first one is true, the second one is true, and if the second one is false, the first one is false, but you can't go in the other direction. Okay, so this is modus ponens and modus tollens. And again, it doesn't really matter that you know these names. It matters more that you understand how these logical deductions work. Okay? So the next one is called disjunctive inference. Sometimes it's called law of disjunction. There's various different names that people give it. But basic idea is if you know that P or Q is true, and you also know not P, you know that P is false, then the only other possibility is that Q is true, right? So if P or Q is true, and you know that P is false, then Q has to be true, right? If I know that I'm going to wear a red shirt or a blue shirt, and I know that I'm not wearing a red shirt, then I have to be wearing a blue shirt, right? It's the only other choice. And similarly with the roles of P and Q switch. So if you know that P or Q is true and you know that Q is false, not Q, then you can conclude that P has to be true. Okay, so this is called disjunctive inference. Okay, the next law is called syllogism, which says that if you know P implies Q and you know Q implies R, then you can deduce that P implies R. So that's saying, like, if you're a dog, then you have hair, and if you have hair, then you're warm in the winter. That means that if you're a dog, then you're warm in the winter, right? You can do this is called syllogism or transitivity somehow. If you know that once you know P, then that will imply Q, which in turn will imply R. So that means we can say P implies R. Okay. Okay, so this is called syllogism. You can string together two implications to make a third implication. Okay, and then some more even very basic properties. So if you know that P and Q is true, then you know that P, you can conclude P and you can conclude Q. And then we also have this contrapositive. If you know that P implies Q, then you can deduce the contrapositive because that's equivalent. You can deduce that not Q implies not P. Okay. Okay. Any questions about what these laws are saying? Okay. So maybe let's do, does anybody want to give just an example with statements of P and Q that illustrate one of these laws? So give an actual statement P, an actual statement Q, maybe a statement R, and show, give an example of using one of these laws to deduce some statement from some other set of statements. So just fill in P and Q with your favorite statements. Alexander? Alexander, do you have any?
No, that even whatever.
Hello?
I won't bought to the hospital. But oh my God,
No, no, no.
oh my
Sorry.
God,
Okay. Sorry. Anybody? Right. So this would be the kind of thing that if you're going to run a workshop on, if you're going to run a workshop on logic, then you'll want to come prepared with some number of examples for this kind of thing. Right. So it will be good to try to write something down. Okay, so let me just do one example just from let me do modus tollens as one example. So example P could be the statement, well, we'll just do the same one before. So it is cloudy, and Q could be the statement, it is raining. So if we're given P implies Q, and we're also given not Q, so P implies Q would be the statement. Oh, sorry. I want the other way around. Sorry. I want P as it is raining and Q as it's cloudy. It's cloudy. So this is if it's raining, then it's cloudy. And then not Q here is the statement, it is not cloudy. Then what can we conclude from this? Well, modus tollens allows us to conclude if we have P implies Q and we also have not Q, then this allows us to conclude not P, which is not P, which is it is not raining. Right? So if it's not cloudy, it's not raining. It's the example we had before. So I see Victor has an example. If Peter and James are both equal in age, if Peter is 10 years old, then James is 10 years old. Right. Yeah, so let's try to put this. I think this is an example of modus ponens. So you could say, for instance, right. So the statement is like you're saying if Peter is 10 years old, then James is 10 years old. Or if Peter is X years old, then James is X years old. And then you're saying if you know, and let's say you're also given that Peter is 10 years old, then you conclude that James is 10 years old, right? So given, if Peter is 10, then James is 10, and also you're given Peter is 10, then you conclude James is 10. And if that seems too easy, that's fine. These are supposed to be easy. These are the fundamental logical laws that you put together to make big things, right? None of these conclusions is supposed to be hard. They're all supposed to be easy. That's why we take them as axioms of a logical deduction system, right? They should be self-evident because you want to take them as axioms. So, so something like this would be an example of modus ponens. If you have the statement, if Peter is 10, then James is 10, that's maybe the same thing as Peter and James are the same age. Then if you're also given that Peter is 10, then you conclude James is 10. Not much more to it. Okay, so let's look at this example valid that we talked about last time, but that we didn't prove, although James sent me a solution to this on WhatsApp. So a valid argument in logic consists of deriving a statement from another statement by using a sequence of rules of logical deduction as on the previous slide. So suppose that we're given all of the following statements. So let's say Laura is in the 7th grade, and we know Laura got an A on the mathematics test or Sarah got an A on the mathematics test. And then we have if Sarah got an A on the mathematics test, then Laura is not in the 7th grade. And we want to use these givens to conclude that Laura got an A on the mathematics test. And we're going to make a valid argument. And we're going to do it first just using reasoning, just writing out a paragraph. And then we'll actually put it into a formal structure, what we sometimes call a two-column proof. Okay? So first, let's just do it. I just repeated everything here, but with a little bit more space. So we want to prove that Laura got an A on the mathematics test. Okay. So does anybody want to try to talk about how we do this proof? At least James, I know you sent me a written solution, which was perfect. So I mean, these things sometimes take a little bit of work. So we want to start with what we know. So let's try to see, are there ways of putting together these statements using our logical rules that tell us something? So sometimes a nice way of starting from this is look for the simplest statement, right? Laura is in the 7th grade. We're given that that is true. Now, once we know that Laura is in the 7th grade, is there something else that we can figure out from that? Well, this fact over here has nothing to do with the 7th grade. So maybe we should skip it for now. But this fact over here says if Sarah got an A on the mathematics test, then Laura is not in the 7th grade. Well, we know that Laura is in the 7th grade. So maybe we should start with something like that. So proof. So since Laura is in the 7th grade, so since Laura is in the 7th grade, the third given statement permits us to conclude that what? Well, if Laura is in the 7th grade, and we know if Sarah got an A on the mathematics test, then Laura is not in the 7th grade. So what can we conclude by combining the first statement and the third statement? We know that Laura is not in the 7th grade is a false statement, right? Because Laura is in the 7th grade. So if this statement is false, what does that allow us to conclude? And we have, if Sarah got an A on the math test, then Laura's not in the seventh grade. But since Laura is in the seventh grade, what can we say about whether or not Sarah got an A on the math test? Anyone? You can write or unmute and talk if you want. The hint is you're going to use modus tollens here. So you have an implication. If this, then that. It's an implication. And now we know that the conclusion here is false. Because Laura is, in fact, in the seventh grade. So what does that mean about whether or not Sarah got an A on the math test? What can we conclude? Anyone want to try? Can write it into the chat if you'd rather not speak. That's fine. Okay, well, let's go back to our laws. I don't want to give this answer. I want somebody to answer it. So let's go back to our laws. What does modus tollens say, right? If you know an implication, P implies Q, and you also know that Q is false, then you can conclude that P is false, right? So if you know P implies Q and you know not Q, then you can imply not P. Great. So that means she didn't get an A. So thanks, James, right? So here we know that if Sarah got an A, then Laura's not in the seventh grade. We know that this here is false. Laura's not in the seventh grade. That means that Sarah got an A on the mathematics test also has to be false. So this allows us to conclude that Sarah did not get an A. And I'll just say this is modus tollens. Okay, great. So Sarah did not get an A. So now let's look at this second statement here, right? We have that Laura got an A on the math test or Sarah got an A on the math test. But we've now already concluded that Sarah did not get an A on the math test. So what does that allow us to conclude? We have an or statement here, and we know that one of the two pieces is not true, right? We know Sarah did not get an A on the math test. So what does that allow us to conclude about Laura? So what does the second statement let us conclude? We have an or over here. Laura got an A or Sarah got an A. We also know Sarah did not get an A. So what does that mean had to happen with Laura? Anyone? She got an A. Exactly, right? So let's us conclude that Laura got an A. And what is the rule that lets us do this? Right? The rule that lets us do this is disjunctive inference, right? If you know that P or Q is true, and you know that one of them is false, then the other one has to be true. Okay? So if P or Q is true and the other one is false, then the other one has to be true. So this is disjunctive inference. Okay? So this is maybe like a kind of wordy proof, a way of doing this. So we're done. And when you're done with a proof like this, you can write QED if you want. Um, okay, so I see. Yes, okay. So these are, and I see, by the way, some examples for Miata. Great. So this is example one is fantastic, right? If a number is greater than 10, then it's greater than 5. 15 is greater than 10, therefore 15 is greater than 5. That's modus ponens, right? You have an if then, and you have that the 15 is greater than 10 is true, then you conclude 15 is greater than 5. So all right angles measure 90 degrees. Angle A is a right angle, therefore angle A measures 90 degrees. Modus ponens again. Exactly, right? If you're a right angle, you measure 90 degrees. Angle A is a right angle. Conclude angle A measures 90 degrees. If all even numbers are divisible by 2 and 8 is an even number, then 8 is divisible by 2. Right, so these are all excellent examples of modus ponens. Right. So these are all good examples of modus ponens. You have an if then, and you have the hypothesis, then you can get the conclusion. Okay. So going back to here, this is kind of wordy. It's a lot of words. So it would be nice if we could write this in a bit more of a mathematical way. So let's try to do the same thing with with what I'm going to call a two-column proof. So what we're going to do is we're going to give names to all of the propositions. So what I'm going to do is I'm going to let P here be the statement Laura is in 7th grade. I'm going to let Q be the statement Laura got an A. And I'm going to let R be the statement Sarah got an A. Right? These are really the three statements that are here. We have being in 7th grade and Laura and Sarah getting A's on the mathematics test. So we start by, how do we do a two-column proof? We start by give names to all relevant atomic statements. Okay, so this is the first thing that we do. So this is maybe the first step. So the second step is we're going to write our givens in symbolic notation. So that means we're given, what are we given over here? Where we're given Laura is in the 7th grade. So that's the statement P. What else are we given? Laura got an A or Sarah got an A. So that's the state, well, Laura got an A is Q, Sarah got an A is R. So we're given the statement Q or R. Given the statement Q or R. And then lastly, we see if Sarah got an A, then Laura is not in the 7th grade. So we're given the statement if Sarah got an A, that's R. Well, R implies Laura is not in the 7th grade. So that's the statement, not P. Chapter 2 is, rewrite the givens symbolically. Yeah, okay. So Princeton also, these are excellent examples of modus ponens. These are great also. Yeah. So we rewrite the givens symbolically. And now the third thing you want to do is you want to conclude What do we want to conclude? We want to conclude that Laura got an A on the mathematics test, right? So that is Q. We want to conclude Q, right? So we rewrite the conclusion symbolically. And so now we don't care about Laura and Sarah and A's in seventh grade and anything like that, right? All that we have now is some symbols. Because what these logical proofs are is you're distilling everything down to the rules of logic. It doesn't matter really what the statements are. That's a distraction. So here, what we're just saying is that if we're given statements P and we're given Q or R, and we're given R implies not P, then we want to conclude Q. That's what this is saying. We've translated this word problem. It's kind of like Keska. Remember, Keska was saying if you have word problems, you translate them into algebra by assigning letters to the various quantities and writing equations. In logic, if you have a word problem, you assign letters to all of the atomic statements and you write out what the givens are and what you want to conclude in terms of logical connectives. So we've translated this word problem here into just saying if we're given P, Q, or R, and R implies not P, then can we conclude Q? And so step 4
Hello,
is
sir.
now hello, yes, Rash? Yep. Okay, so step 4 is writing a two-column proof, which I'll do on the next page. So so how do you do a two-column proof? You're used to this in geometry. You can do the same thing in logic. So here, what's a two-column proof? Here we have, I'm going to just call this the number. And then here's the statement. And here's the reason or the justification. So I start with all my givens. And I'm just going to number the statements 1, 2, and 3. It's helpful for doing this. So the statements that we have are P, Q, or R, and R implies not P. So I'm just going to copy these down. P, Q, or R, and R implies not P. And the reasons, this is just given, given, given. Okay, there's nothing to say here because we're allowed to assume this from the beginning. Okay, so what do we do? Well, if we go back to our proof here, we said that the third given statement allows us to conclude that Sarah did not get an A by using modus tollens. So that's, a lot of words here. But if you go here, what is the third given statement? It's R implies not P. And we also have P, which means that not P is false. So this allows us to conclude not R. So in a statement reason proof, all you have to do is write not R. And what's the reason? The reason is modus tollens. And you can cite the numbers of the statements that you want to cite in order to make that true. So it's really modus tollens applied to statement 3 and statement 1, right? Because 3 is your implication. Statement 1 is telling you that the second part is false. And using modus tollens will tell you that the first part is false, right? So instead of R, you can conclude not R. So we want to conclude Q. What did we do in our actual proof? Well, in our actual proof, we said, since Sarah did not get an A, the second statement lets us conclude that Laura got an A. So we're using the second statement, and we're using disjunctive inference on the second statement. So how do we say that symbolically here? Well, I'm going to add another row that's going to be 5. Well, the point is we're using not R, and we also know Q or R. So disjunctive inference tells you that if you have not R and you have Q or R, then what has to be true is that Q is true, right? Because you have an or statement and one of them is false. That means the other one needs to be true. So in this case, you can just conclude Q by using disjunctive inference. And what are you using for it? You're using your disjunction, which is line 2, and your false statement, which is line 4. So this is line 2 and line 4. Okay? And now you're done. You actually don't need the rest of the table. The proof is already done, right? What did we want to do? We wanted to conclude Q as desired. We started with these implications and we wanted to conclude Q. So we conclude, or we have, maybe I'll say we have derived Q as desired. Okay. Okay. So you've distilled this entire paragraph proof where you're talking about seventh grade and A's and math tests and all of this irrelevant stuff into its logical essence. And its logical essence is this. It doesn't matter what the statements P, Q, and R are. If you know the statement P, and you know the statement Q or R, and you know the statement R implies not P, then from that you can conclude not R, and from that you can conclude Q. And Q was exactly the statement that we wanted to derive, right?
Teresa,
Yes, Rash. Hello?
uh,
Yes.
yeah, they never give me hot on phone like reason the
Okay,
network.
yes. Sorry about that.
Yeah, the network from my own side.
Yeah, no, it seems like you've had to go
They
in and
doing
out quite a lot.
doing off and on. So yeah, in case
Okay.
yeah.
Okay. So hopefully, at some point you'll be able to do the recording and look at the notes. They can't go back too much now because we're almost out of time. Okay, so are there any questions about how this proof works? It's kind of, if you haven't seen this a lot, then it's maybe a little hard to get started. But once you do it a few times, then you appreciate how simple it becomes. And you don't need to write very much. You can just write it up in this very efficient way, and you don't need to write a lot of extra words. Yes, Miyata?
Yes, Doc. I really want to understand this table better. I still have some doubts because I did not continue with the class. There was a time I slipped out here.
Hmm. Okay,
I missed it.
so just to review the table. Okay, right. So just briefly, okay, so the first is just the number. We just number the statements in order. That's just so that we can refer to them. The first three lines are just the given statements. It's what we're allowed to assume. So they're just given. And then we need to figure out what are our conclusions. Well, what did we do? We knew that P was true, and we knew that R implies not P is true. These are both given, right? So the point is any statement you write here has to be true, right? You're only writing true statements here. And you want to know that if your givens are true, then ultimately you want to get to your conclusion. You want that to be true too. So on the way there, you're only allowed to write true statements. Okay, so the first three statements are true because they're given to you. The next statement is true because you're using the valid logical implication of modus tollens, which is that if you have an if-then statement and the second part is false, and we know that it's false, right? Because P is true, so not P has to be false. That means you can conclude that the first part is false. So from this, we're concluding that R is false. Another way of saying that is not R, right? Not R is true, right? We only write true statements. In this column. Okay, so we only write true statements here. So here we have an implication that's true, and the second statement is false. That means the first statement also has to be false. That's modus tollens. And what I do is I write 3-1 here to just remind the reader it's not just modus tollens in the abstract. It's modus tollens applied very specifically to line 3 and line 1. So it shows the reader where you're doing it. You have line 3 as your implication, And line 1 is what tells you that the second part here is false. And so from that, you conclude that the first part is false. So there's your modus tollens applied to line 3 and line 1. That allows you to conclude not R. That's a valid implication. Moving along, well, now we know that Q or R is true, and we know that not R is true, which means that R is false. So if we have an or statement that's true, and one of the pieces is false, that means that the other piece needs to be true. That's called disjunctive inference. Okay? And so what we conclude is that Q is true. It's disjunctive inference, but again, I don't just say disjunctive inference in a vacuum. I give the numbers 2, 4 to direct the reader to which statements I'm using. I'm using the statement 2, which is Q or R, and I'm using statement 4, which is not R. And when I combine them together, Q or R along with not R, what that allows me to conclude is Q, right? Again, if I'm eating rice or if I'm eating cassava and I know I'm not eating rice, that means I'm eating cassava, right? If one of the things is false, then the other thing is true. Okay, so disjunctive inference here is going to tell me that Q is true. And you just put in these numbers to direct the reader which statements are you using when you make your disjunctive inference. Okay, and what we wanted to prove was Q. So once we write down Q, we're done. We start with the givens. We want to get to the conclusion. In this proof, there was a small a small step that we had to make in order to get there.
Thank you,
Okay,
Doc.
sorry, Miata. Is that helpful?
Yes, I was saying thank you.
Okay, you're welcome. Okay, so we're not going to have time. We're not going to have time for this one. This is a challenge. I'm going to give you this as homework. Okay, but the idea is to try to do this as a two-column proof. And I'm going to say that there will be 6 atomic statements. So you're going to have P, Q, R, S, T, U. Or you can use whatever letters you want. Okay, so this is a little tricky. We'll go over it. We'll go over it slowly next time. But promise breakers are untrustworthy. Wine drinkers are communicative. A person who keeps his or her promises is honest. No teetotalers or pawnbrokers, and all very communicative people are trustworthy. You want to prove that all pawnbrokers are honest. Okay, so this is a bit of a challenge, but I'll let you think about it. This is due to Lewis Carroll, who was a mathematician who also wrote Alice in Wonderland, but was, a British mathematician in the 1800s. So he has a bunch of these kinds of logic problems. And the other hint is you're going to use lots of syllogism. Right, remember, that's if you have P implies Q and Q implies R, you conclude that P implies R. Okay, but I'm not going to talk about this now because we don't have time. What I do want to do is I do want to spend a little bit more time on logic next time before we go on to circle theorems. And I don't have time to cover all of these. So there's proof by contradiction, logic and computer science, open sentences and quantifiers, and further practice with logic word problems. So what I'm going to do is I'm going to make a poll that I'm going to let everybody vote. So which topics vote for 2? Okay, so the choice, I'm going to want multiple choice, right? So choice 1 is going to be contradiction. Choice 2 is computer science. Choice 3 is open sentences and quantifiers. And choice 4 is word problems, like these ones that we're doing. Okay, so, and now I'm going to save this. Okay, and now I want to just launch this poll now. So how do I do this? Okay, untitled poll. Okay, that's good. Saved it, save. Save as meeting poll. Okay, good. And so now I think I can launch it. Yes. Okay, so did everybody get a poll? Okay, so if you got this, just in the next minute, maybe everybody can vote for two topics, and the top two vote getters will be what I discuss next week. Okay, so vote for two out of four. So we'll give, a minute or two for everybody to respond to the poll. Okay, okay, get some more votes. So I have 6 out of 13 have participated so far. Okay, so maybe one more minute for everybody else to vote. Okay, so I'm going to leave this open until the poll titles 2 minutes. So yes, if you're voting, please vote on the poll in Zoom. That way I can accumulate all of the votes. Okay, don't just vote in the chat. You should be able to tick two boxes, and that's going to be your vote. This way I can keep track of all of them. Okay, so I'm going to close the poll in 20 seconds. So if anybody hasn't voted yet, please vote. Otherwise, I'm going to close the poll. Okay. Again, please vote in the poll by checking boxes. Don't write your answer. Your answer won't be tallied if you write it in the chat. And just check your boxes in the poll. Okay, all right. So I'm going to end the poll now. Okay. Okay, so I'm going to end the poll now. So it looks like the winners are contradiction and so proof by contradiction and open sentences and quantifiers. Okay, so that's what I'll focus on next time. Okay, so share the results. This is the results. Okay, so that contradiction got 3 votes, and open sentences and quantifiers got 5 votes, and the other topics got 2 votes. So so these will be the two topics that we do next time. Okay, great. All right, so thank you again for your attention. So next week on February 26th, we'll finish our mini workshop on logic, and we'll begin planning a mini workshop on circle theorems. And just as homework, I just want to remind you that we have these exercises. Show that P implies Q is equivalent to not Q implies not P using truth tables. And then optional is the challenge exercise from before. Okay, so optional is this challenge exercise over here. This one due to Lewis Carroll. Okay, so a last chance if anybody hasn't typed their name in yet for attendance, last chance to type your name so that I have your record, and then I will stop the recording. And thank you as always for your attention, and I will speak to you next week. Okay, I'm going to stop the recording now. Very last chance, type your name, but I think everybody has so far. Okay. Good. All right.